Hi, and welcome to OzGrav's YouTube channel. So OzGrav is the ARC Center of Excellence for Gravitational Wave Discovery. And this is the next in our series of live stream talks from our researchers. Today, we are bringing you a talk by Ilya Mandel. These talks are to showcase the amazing work that our researchers are doing and give them the opportunity to share their science. So I'll just tell you a little bit about Ilya before I pass off to him. He received his PhD in physics from the California Institute of Technology in 2008 with a specialization in gravitational wave astronomy under the supervision of Kip Thorne. He carried out postdoctoral research at Northwestern University and at the Massachusetts Institute of Technology as a National Science Foundation Astronomy and Astrophysics postdoctoral fellow. Ilya arrived at the University of Birmingham in the UK as a lecturer in 2011 and was promoted to Professor of Theoretical Astrophysics in 2016. During this time, he established himself as one of the leaders in the emerging field of gravitational wave astrophysics, focusing on the sources of gravitational waves, data analysis challenges posed by current and planned gravitational wave detectors, the astrophysics of compact object binaries, and ways in which upcoming observations of gravitational waves can aid our understanding of this astrophysics. Fortunately for us, in 2019, Ilya joined Monash University outside of Melbourne, Australia, as a professor in the School of Physics and Astronomy. He is a Chief Investigator with OzGrav, and in addition to that, he has two awesome kids, and by his own account, writes terrible poetry, which I'm sure is not terrible. I'm sure it's just as awesome as your kids. So what we're going to do is Ilya will give his talk, and then during the talk, please feel free to engage with the chat on the YouTube channel in order to ask any questions you may have, and we will have time at the after the talk to pass those questions on to Ilya so that he can answer them for you. So without any further delay, I would like to introduce again Ilya Mandel and his talk, Singing Binaries, Listening to the Chirps of Black Holes.
Thank you very much for that kind introduction, Jackie, and thanks to everybody who is listening in. So as Jackie said, I try to think about the sources of gravitational waves that, as you've probably heard, instruments like LIGO and Virgo have detected over the last few years. And my personal interest is in understanding how these gravitational waves come about, what are the sources that generate them, and what we can hope to learn about those sources by observing gravitational waves. So let me start by asking how we generally go about observing the universe. So we astronomers staring up at the sky, seeing these beautiful stars above. Of course, modern astronomers are far more sophisticated than that, so we don't just stare up at the sky. We get a telescope and we attach it to a computer and we download a bunch of data, and then we actually stare at our computer screens because our eyes aren't good enough anymore to stare up at the sky and see the exciting things because we're too used to staring at computers. Now, that works well, but as we'll see, it doesn't work well in all cases in a moment. But before we talk about that, let's step back for a second and talk for a second about gravity. So you all know the story. Isaac Newton was sitting under an apple tree in Cambridge. An apple fell on his head, clearly jarred something, and as a result, supposedly Newton came up with this universal law of gravitation, namely that any two massive objects attract each other. They attract each other with a force that is proportional to the square of the distance between them. That's all well and good, but there is something a little funny about this. There's this notion that there's this instantaneous force that acts at a distance. So somehow, miraculously, for example, if the sun were to explode in supernova, right now, which it will never do, the sun is too light to explode in supernova, but let's suppose it did, we would be able to sense it immediately because we would somehow magically know momentarily that the gravity has changed, even though we would not be able to actually see it for a good 8 minutes, because that's how long it takes light from the sun to reach us here on Earth. There's something funny about that, and Einstein certainly didn't like it, and he therefore suggested a different view of thinking about gravity. Gravity is something that distorts space and time, and then objects travel in this distorted or curved space-time on the straightest possible path they can, which of course, since the space-time itself is no longer flat, actually takes them on curved objects, like this little picture of a massive object creating this funnel in a space-time and some satellite going around it on what it tries to make a straight orbit, but actually ends up being a circular orbit because of the distortion of the funnel, distortion of the space-time. And there have already been a number of tests of general relativity. Perhaps the most famous one is actually predates Einstein. It was due to the extra precession of Mercury, which is moving in a slightly eccentric orbit around the sun, and you can see that it's not repeating the same orbit as it should under classical Newtonian gravity, but direction of the orbit is changing a little bit from one orbit to another, and they're really doing a little bit, something like 1/100th of a degree per century, but nonetheless, that is in principle observable and can be explained by general relativity, cannot be explained by Newtonian physics. But there are other cases as well, although in general, of course, Newton's approximate theory of gravity is pretty good, and perhaps you might say that actually in everyday life we shouldn't really care. And one of them is actually the global positioning system, or GPS. If you are driving somewhere, which of course you shouldn't be doing right now if you can avoid it, stay at home and be safe. But once you are allowed to go out again and are driving or being driven somewhere and are using a map on your phone, turns out that that map is, we include corrections from general relativity in the kind of calculations that we do based on the motion of satellites that are sending their triangulation signals to your phone, which is how GPS works. If you didn't include GR in those calculations, your Google Maps would fail after just a few hours. Electromagnetic waves from distant stars. Maybe we even learn something about gravity, and maybe we actually black holes. Well, there you go. We've seen a black hole. No, it's not that your or my video feed has cut out. It's actually that this is what black holes look like. Black holes are utterly and completely, not even light can escape from the pull of a black hole. So there's no hope in seeing a black hole, right? Well, maybe not quite. Maybe there are ways to look for them. So how could you see a black hole? Well, you can't see the black hole itself because gravity is just too strong, but maybe you can see other things going around the black holes. And that's in fact the case. So here's a picture from the movie Interstellar, and I'm bringing this in for a reason because founders of the sort of modern revival of general relativity and one of the people who won the Nobel Prize for the events. He was also actually the originator of the movie Interstellar and the consultant on that movie and a producer on that movie. And here you see a picture from that movie that shows what some material moving around a massive black hole in what's called an accretion disk might look like. And it looks kind of below and in front of the black hole. Actually, the disk is all in the plane that's perpendicular to the plane of the screen, there is no material above or below the black hole. You're looking at this disk of hot material moving around the black hole edge on, but the parts of the disk that are behind the black hole are being gravitated. That light from the disk is coming in either behind or below or above the black hole. Here's another way of looking for black holes. These are stars in the galactic center, the center of our galaxy, the Milky Way, moving around the black hole. And you see that these stars, they've been observed here for something like 20 years, and some of them during that time have gone on fractions of orbits, some have gone on complete orbits around something that looks very dark. There is no actual object at the center of this image, nothing that is visible, and yet if you calculate the trajectories of these stars, you realize there must be an object there that has a mass of about 4 million solar masses. You can see stars that are just a few solar masses at this distance using the sensitive telescopes that we have today, and yet you cannot see this very massive object that's 4 million solar masses. How can that be? The only possible explanation is that there is a massive black hole at the center of our galaxy. And in similar ways, we also know from stars moving around lighter black holes that there are quite a few black holes scattered around our galaxy with masses of 5, 10, 15, perhaps as high as 20 solar masses. So actually, our galaxy is awash in black holes, and so are the galaxies around us. And that brings about a very exciting opportunity, an opportunity to observe in something very different from light, to observe in gravitational waves. So gravitational waves are a prediction of the general theory of relativity. And the idea is that when massive objects circle around each other, they create ripples in the fabric of space-time, similar to what you might see if you drop a little pebble into a pond and you have ripples propagating out, except the gravitational waves propagate at the speed of light, and you only get significant amounts of gravitational radiation when you have truly massive objects like black holes moving very close to each other at very high speeds, close to the speed of light. And then what gravitational waves do, they don't allow you, they're not directly visible. What instead they do is they stretch and squeeze space perpendicular to the direction of motion. So all you have to do if you want to impress somebody, for example, by how tall and slim you are, is to wait for a gravitational wave to pass by, and it will stretch you this way and squeeze you this way, and you might look very impressive, but two things. One is you have to make sure the person is looking at you in the right half cycle of the gravitational wave, because the next half cycle, you'll instead be broader this way and shorter. And the other problem is you better hope the person has very good vision, whoever it is you're trying to impress, because typical gravitational waves that we're hoping to observe are stretching and squeezing you by 1 part in 10 to the 21st power. So that's 1 with 21 zeros behind it. That's a tiny amount. And that means that it's almost hopeless to observe. And so for a long time, people thought they were purely a theoretical prediction that would never be observed in practice. But actually, it turns out that there may be a way to do this. And this was an idea that Kip Thorne and a couple of colleagues, including Ray Weiss from MIT and Ron Drever from Glasgow and then Caltech, had, that you might be able to build a detector, which was ultimately called LIGO, Laser Interferometer Gravitational Wave Observatory, that would use lasers to very precisely measure distances between masses. And when gravitational waves would come by, they would set those masses moving. And when the masses would move, a very sensitive system would allow you to detect the motion of those masses and therefore observe the gravitational wave passing through. So it's using something called the Michelson interferometer. And here you see a little schematic of light from a laser coming through a beam splitter, going out the two arms of the detector. The arms are not drawn to scale here. They're actually about 4 kilometers long in the case of LIGO detectors. Light bounces off to masses attached to pendula, to mirrors attached to pendula at the ends of the beam tubes. The beam tubes are all vacuum. It's a very fancy system, costs several $100 million to build. But at the end of the day, what you're looking for is a dephasing, a change in the relative phase of the light coming back from the two arms, which is telling you that the length of the two arms have become different by something like 10 to the minus 17th of a meter, so a tiny fraction of the size, not just of an atom, but of an atomic nucleus. That's the kind of sensitivity you're hoping to get in order to be able to detect gravitational waves. And so for a long time, it looked like it would be incredibly challenging trying to get this kind of sensitivity, trying to measure the length of 4-kilometer arms to a precision that's less than the size of an atomic nucleus. And there were all kinds of challenges, and this is why there was a huge collaboration set up to do this, because something like 1,000 people were needed to build the instruments and the data analysis effort to search for these signals. But and there were all kinds of challenges to overcome. So here are various sources of noise for LIGO, which include, by the way, local earthquakes, and include some unexpected sources of noise. Like, for example, here's a local ranger and the site in Washington State in the US, who apparently somehow didn't see the 4-kilometer long concrete beam tubes and managed to run into them. I'm not sure how good the ranger was at doing their job if the 4-kilometer beam tubes were too invisible, but nonetheless, that's also a noise source because it shakes the mirrors a little bit when things run into the beam tube. So all sorts of things that these people had to account for. And in the end, in 2016, a paper was published claiming a direct observation of a gravitational wave merger. So this was a truly exciting event. Gravitational waves have been seen for the first time. And by the way, you can see that there's a huge author list, but the author list was, at least at that time, missing people whose last name would start with an X. So and I was told by a colleague who works at CERN that until you have somebody starting with every letter of the alphabet in your author list, you're not really a proper big collaboration. So if you're listening to this and your last name starts with an X, there's still space in LIGO for you. You should very much consider joining, even if it doesn't start with an X. I'm sure they're looking for a few more good women and men to join. This was what the signal looked like. So you can see it's pretty noisy, but there's a clear sinusoidal shape to it and a chirping shape, because as the two objects, the two black holes that are spiraling around each other, which is what LIGO is trying to observe, are getting closer and closer together, they go through this chirp where the amplitude of the signal and the frequency of the signal are going up. So let's try to play this. There you heard the chirp heard around the world. This wasn't quite the same signal as the one LIGO had observed. This is a neutron star, 1.4 solar mass neutron star, spiraling into a 10 solar mass black hole. But again, you hear this characteristic chirp. Here's another one just for fun. This is from a 14 solar mass black hole, spiraling into a 50 solar mass black hole. It's actually in the audible band. Of course, you couldn't hear it because sound doesn't travel through space. And in any case, the amplitude would be far, far too low for you to be able to hear. But what you can do is detect it using the instruments we just discussed, the LIGO instruments. And as you may have heard, although the general feature of this chirp-like signal was similar for the two sources I just played, there were also differences in the rate of the evolution in time. And that also means you can not just detect the signal, but learn something about the properties of the source from the observed signal, such as the masses and even spins, the rate of rotation of the black holes or neutron stars. So here was a cartoon published in the New Yorker magazine shortly afterwards, a couple of birds sitting on a branch and asking, was it you I heard just now, or was it two black holes colliding? So now you know what the game they were playing. They were reminding their clever readers that when two black holes collide, they make a chirp-like signal. So maybe it sounds a bit like a bird. So by now, of course, LIGO has seen not just one source, but a dozen published sources, and maybe something like 50 sources that are still waiting in their pipeline they've already detected but haven't yet told the rest of the world about. And of course, now that brings up interesting questions about how those sources were formed. But I suspect that that's probably a discussion for another time. So let me actually stop here and see if there are any questions.
All right. I'm just gonna. So we had to briefly pause your video there for a moment because we were getting a couple glitches. But what I'm going to do is, there we are. There you are back. So yeah, we did have a couple questions. So what a question was that came in: do gravitational waves affect light?
So in principle, gravitational waves do affect light, and it's generally a very weak effect, but there's at least one way in which we are actually trying to use the effect of gravitational waves on light to study the universe, and it's called pulsar timing arrays. So pulsars are neutron stars that are very rapidly rotating and that have a magnetic field that's a little bit misaligned with their axis of rotation. So even though they're always emitting a constant beam of radiation, it looks like they're pulsing because imagine this is my fist is my beam of radiation, and now it's pointing towards you, and now I'm rotating, it's pointing away from you, and now it's hard to rotate while sitting on a chair, but let's pretend that I succeed in finishing my rotation, and now it's pointing towards you again. So this looks like a pulse, and the regular pulsations comes about from the regular constant rate of rotation of the neutron star. But imagine now there are gravitational waves coming from some very distant, very massive black holes, having nothing to do with the pulsar. The pulsar is in our own galaxy, relatively nearby. There are two massive black holes somewhere in a distant corner of the universe. But the photons coming out from this pulsar, the electromagnetic waves, the light coming from the pulsar, is surfing on the gravitational waves, because the space or space-time has these ripples in it from these massive distant black holes merging together. And as the photons surf on these waves, on these ripples, the time of arrival changes very, very slightly. So in general, for the best measured pulsars, we can predict their pulsar, when the pulsar will arrive, years ahead to an accuracy of less than a millionth of a second, an accuracy of maybe 10 to 100 nanoseconds. And sometimes we see that somehow our predictions aren't quite right, that there is some extra residual in the observed arrival times. And that allows us, in principle, to look for gravitational waves at much lower frequencies than LIGO can sense. LIGO is sensitive to gravitational waves at a frequency of 100 hertz. Now we're talking about gravitational waves with periods of a year or frequencies of maybe 30 nanohertz from very massive black holes. But those can be detected in this way through pulsar timing arrays. And that's something that OzGrav is also heavily involved in.
Great. Yeah, it's amazing how scientists have been able to reach such accurate measurements, not only with pulsar timing, but also with the detection of gravitational waves. And I really hope that's one of the takeaways for the public from this talk today. So one of the questions I always like to ask our scientists is, what future possible discovery are you most excited about? Something that's kind of on the horizon.
So I think there are several things that are very interesting. So one thing that's very interesting is that so far all of the LIGO observations have confirmed that the general theory of relativity is correct. But that doesn't mean that it's actually completely correct, in the sense that it doesn't mean it's completely the right theory of physics, because we know there are some issues with general relativity. For example, it's very hard to get general relativity to mesh with quantum mechanics. And so we know that there must be some level, maybe very, very close to the singularity that's inside the black hole, where densities become incredibly large, maybe near the horizon of the black holes. There must be something where maybe general relativity has to be modified. And it would be very exciting if future, even more precise observations, because LIGO is gradually getting improved, and there are already plans for future detectors, including maybe one that someday might be located here in Australia. There are ideas of how to make these detectors even more sensitive, and then maybe we could actually probe whether general relativity is in fact the correct theory of gravity. And I think that would be hugely exciting, or at least where it might break down and what it might tell us about how quantum mechanics and general relativity might interact.
All right, that is very exciting. So what we're going to do is we're probably going to go ahead and wrap up there. Thank you, Ilya, for a great talk. It's, and some excellent animations, and the chirps are always a fun bonus. So in 2 weeks, OzGrav is going to have another talk by one of our researchers at University of Sydney. So we'll have Dougal chatting about bursts, jets, and waves, probing the universe with gravitational waves and light. So Dougal is a PhD candidate with OzGrav at the University of Sydney. So that's going to be coming on the 4th of June. So again, if you have any further questions, you can always go to the OzGrav website, where you can also find our documentary on gravitational waves and the work that we do as well, if you want to learn more. So thank you, Ilya, for joining us today. And we really enjoyed that talk. Thank you.
Thank you.